Hello everyone, this is Dr.Prashanthi, Assistant Professor, Department of Chemistry from Government Degree College for Women, Karimnagar. Today I am going to discuss about the topic photochemistry. What is photochemistry? Let us have some introduction about the topic. Photochemistry is the study of chemical reactions that proceed with the absorption of light radiations by atoms or molecules and its effect on the substance. That is, the effect of the absorption of light radiations on the substance is called as photochemistry. That is, photochemistry is the study of chemical reactions which occur in a molecule or an atom or a substance by the absorption of light radiations. And light is a type of electromagnetic radiation, a source of energy, and light must be absorbed by a chemical substance in order to perform a photochemical reaction. And this study of photochemistry helps us to know the changes when a molecule absorbs radiations, what happens after the absorption of radiations by the molecule. Let us have some more introduction. That is, see, energy changes, actually the energy changes in an atom or a molecule may be carried out by two methods. One is by changing the temperature, that is they are called as by changing the temperature means there involves the thermal energy, and this gives rise to the thermal chemistry, and it causes a continuous increase in the energy. And the another type is by the absorption of electromagnetic radiations. This type gives rise to photochemistry. So first type is by changing or by carrying changes in the temperature, which leads to thermal energy and thermal chemistry. Another type is by the absorption of radiations. This gives rise to photochemistry. And the chemical effect associated with the emission or absorption of these electromagnetic radiations are explained in photochemistry. And the reactions which can be brought about by light radiations are called as photochemical reactions, and generally deals with the rate and mechanism of reactions taking place due to the exposure of light, that is mostly by the absorption of radiations from UV and visible range leads to photochemical changes. Chemical reactions occur only when a molecule is provided the necessary activation energy, and this activation energy is provided by the light in photochemical reactions. Then let us see how what will be the interaction of radiation with the matter. See, suppose when an atom or a molecule is exposed to radiation energy, that is here UV and visible region of the spectrum, the individual molecule gets excited to an excited electronic state. See, when the energy is supplied by these light radiations, that is by UV or the visible range radiations are absorbed by the molecule or an atom, it gets excited to the higher energy levels. That is, an electron is promoted from bonding molecular orbital to anti-bonding molecular orbital. The electron gets promoted, and the amount of energy that such radiation contains depends upon the wavelength and the frequency. So according to Planck's theory, the energy absorbed by a molecule is E is equal to h nu, and mostly the radiations of shorter wavelengths, that is visible radiations, contain more energy. Visible radiations are of shorter wavelength and they contain more energy, and UV radiations contains energy nearly 143 kilocalories per mole. This energy is sufficient to excite the molecules to higher electronic states. That is, the energy of the radiations of visible light and UV radiations are sufficient to excite the molecules or to excite the electrons present in an atom or any molecule to higher electronic levels. Suppose, for example, hydrogen atom. Suppose if you take a hydrogen atom, okay, hydrogen atom is is containing only single electron in 1s orbital. Okay, this absorbs visible radiation and excites the electron is excited to 2s orbital when it absorbs visible radiations. And for example, in molecules, the absorption of visible radiation excites the electronic state, which involves the excitation of electron from bonding orbitals to anti-bonding molecular orbitals. So, UV and visible radiations are sufficient to split the chemical bond present between the molecules. Therefore, UV and visible radiations. So, UV and visible radiations are called as photochemical radiations. Therefore, these are called as photochemical radiations, and these are used in studying the photochemical reactions because these radiations are sufficient to excite the to undergo an electron from to get excited from lower levels to the higher levels, and these are sufficient to split the chemical bond present between the molecules. Therefore, these are called as photochemical radiations. And suppose when an organic compound is heated, suppose till now we have discussed about the absorption of UV and visible radiations. Okay, suppose if a compound is heated, okay, the molecular motion increases, the number of collisions between the molecules increases, and the vibrational motions within the molecules increases. So, at particular temperature, that is at particular higher temperatures, the vibrations becomes so energetic that the bond between the two nuclei breaks. Here the thermal excitation takes place, that is thermal excitation introduces energy here, and the energy distribution is in such a way that most molecules have about the same amount of energy. Okay, in case of thermal excitations, the molecule will be heated where the collisions increases, vibrational motions increases, and at higher temperatures they become so energetic, that is they become more, which makes the bond to get breakage between the two nuclei. Okay, this is in case of thermal excitation, and here the energy distribution will be equal, and most of the molecules are involved, they contain the same amount of energy and they are involved in the this process. But in the case of absorption, or in the case of photochemical radiations, the absorption of radiation is limited to only individual molecules. Okay, and they only get excited to the electronic states. Similarly, from bonding molecular orbital to anti-bonding molecular orbital. That is, in this case, large amount of absorbed energy is limited to only a single molecule. But in case of thermal excitations, most of the molecules have about the same amount of energy and most of the molecules are involved. But here in case of photochemical radiations, a single molecule or a single photon is absorbed by single molecule only. Okay, this we will study this clearly in the laws of, under the heading of the laws of photochemistry. So the like this we have some differences between the thermal energy and photochemical energies, and let us see what are those once again. Differences between thermal and photochemical reactions. Thermal reactions, photochemical reactions. Thermal reactions involves absorption or evolution of heat. Here there is no question of absorption of light in case of thermal, only it is dealing with the heat only. Photochemical reactions, they involve the absorption of light. So in order to undergo a photochemical reaction, absorption of light is compulsory, and thermal reactions can take place even in the dark or in the presence of light. And for photochemical reactions, the presence of light or absorption of light is compulsory. And third point, temperature affects the rates of thermal reactions. And in the case of photochemical reactions, temperature does not have any effect, they are independent of the temperature. And in thermal reactions, the intensity of the light does not affect the rate of these reactions, as these thermal reactions are not involving in any radiations. Therefore, the intensity of light has no effect on the rates of the reactions of thermochemical reactions. And in case of photochemical reactions, the intensity of the absorbed light affects the rates of these reactions. And in thermal reactions, the free energy changes is always negative, but in case of photochemical reactions, it may be negative or it may be positive. That is, in the free energy changes of photochemical reaction may vary with the reaction. That is, for example, spontaneous photochemical reactions show free energy change, shows a positive free energy changes. That is, for example, decomposition of HCl into hydrogen and chlorine, and photosynthesis of carbohydrates in plants. In these cases, these are spontaneous reactions which occur under the influence of the radiations, and therefore here in these two reactions the free energy changes are found to be positive. And next point, thermochemical activation is not of selective nature, but photochemical activation is highly selective. That is, in case of photochemical reactions, a particular molecule absorbs radiations, and that molecule only undergoes some chemical change or some photochemical change in case of photochemical reactions. In this way, we have some differences between thermochemical reactions and photochemical reactions. Next, laws of photochemistry. What are the laws of photochemistry? All the photochemical reactions are governed by two basic laws known as laws of photochemistry. What are these two laws? Let us see. Grothes-Draper law, and next second one is Stark-Einstein law. First one is Grothes, or it is also called as first law of photochemistry, Grothes-Draper law, and the second law of photochemistry is Stark-Einstein law. Next, Grothes-Draper law. What is Grothes-Draper law? See, when light falls on any body, part of it is reflected and part may be transmitted, and some part may be absorbed. That is, when a light falls on any molecule or any body or any substance, some part of it is reflected, some is transmitted, and some part is absorbed. And the important point is that the light should be absorbed in order to bring a chemical reaction. So, based on this, we have two laws. This is Grothes-Draper law and Stark-Einstein law. And Grothes-Draper law defines that only those radiations of light which are absorbed by a reacting substance are effective in producing chemical change. That is, the light is absorbed by any substance, but some part is reflected, some is absorbed, some is transmitted. So, only the part that is absorbed by the substance are effective in producing the chemical change. And according to this law, all the absorbed light radiations need not be used to bring the chemical reaction. See, the substance is absorbing a light, okay, and this is not necessary that the absorbed light should bring the chemical change. Okay, that is not a compulsory. If a substance is absorbing light, it should undergo a chemical reaction compulsorily. Okay, no need of this. This is not a compulsory. That some reactions they absorb light and they undergo chemical reactions, but in some cases they may not undergo any chemical reaction, and these radiations are used to increase the kinetic energy of the molecule, and in some cases some are re-emitted, and in some cases they are re-emitted. And see this particular law, or Grothes-Draper law, this is the basic law of photochemistry, and it gives no idea of the relation between the light absorbed and the substance undergoing chemical change. That is, it may absorb, the substance may absorb light, but it may not undergo chemical change. Therefore, this law is purely qualitative in nature. Suppose for example, if you take uh, potassium permanganate solution, that is a KMnO4 solution. Potassium permanganate solution, it absorbs light radiations, but here any chemical change is not produced. That is, potassium permanganate absorbs light radiations, but it does not undergo any chemical change. Suppose for example, if you take another example, suppose when white light is passed through alkaline solution of cupric tartarate, okay, when the light is passed through this alkaline solution, the substance undergoes photochemical reduction to, this undergoes reduction to cuprous oxide, undergoes reduction, and means here the chemical change is occurring, but the absorption spectrum shows that this molecule is absorbing infrared radiations, okay, orange and ultraviolet radiations, and visible radiations, that is orange with the wavelength of orange light. These are absorbed by the solution, but only ultraviolet light, which is covering a small range of wavelength, is able to bring about the photochemical change. Hence, ultraviolet light is the effective light for this photochemical change from cupric tartarate to cuprous oxide. That is, only those radiations which are absorbed by the reacting substance are effective in producing chemical change. It may absorb some other radiations from the light, but from the spectrum, but only those which are absorbed by the substance are effective in producing the chemical change. And the next point is, even though it is absorbing the even though a substance is absorbing the light, it is not necessary for the substance to undergo the chemical reaction. It may absorb light and it may undergo chemical reaction, and if it absorbs light, it may not undergo a chemical reaction. Okay, this for example is absorption of light by potassium permanganate. It absorbs radiations, but it is not undergoing any chemical reaction. Okay, this is Grother's Draper law. So, according to this law, only those radiations of light which are absorbed by the substance are effective in producing the chemical change, and as it is not giving any relation between the light absorbed and the substance that is undergoing chemical change, this is purely qualitative in nature. Let us see what is the second law. Second law is Stark-Einstein's law. This is the second law of photochemistry, and this states that in a primary photochemical process, each atom or molecule is excited by the absorption of one quantum of radiation. 1 mole of reactant absorbs 1 Einstein of radiation. So, according to this one molecule absorbs 1 photon of radiation only. Okay, 1 molecule of reactant absorbs 1 photon of radiation, which is called as a 1 Einstein. 1 Einstein or 1 photon or 1 quantum of radiation. See, and this law is applicable only to the primary process. That is, primary process means the process in which the substance absorbs energy and gets excited to the higher levels. See here, this law shows relationship, that is, one molecule absorbs 1 photon of energy. 1 molecule absorbs 1 photon or 1 quantum or 1 Einstein of energy. This is showing relation between the number of reacting molecules and the number of quanta of light absorbed. Therefore, this law is applicable only to primary process, and therefore this is quantitative in nature. And this is applicable only to the primary process, that is only to the excitation of atom by the absorbing radiation only. See, in the photochemical reactions also they include two processes, that is a primary process and secondary process. Primary process means absorption of radiations by the substance and excitation, and in the secondary process means the changes that occur after the absorption. Okay, the changes that occur after the absorption means maybe a chemical change, that is after the absorption of light radiations by the substance, the electrons in it gets excited to the higher levels. This happens in the primary process. Next, in the secondary process, the excited electron may undergo some chemical change or may not undergo some chemical change, and some other process can occur which we can study later under the topic photophysical processes. Okay, so the important point of this law is that in the primary photochemical process, each atom or molecule absorbs radiation and is get excited by the absorption. This occurs only in the primary process only. And for primary process here, the number of molecules excited is equal to the number of protons. Suppose if one molecule is absorbing 1 photon of radiation, if 10 molecules, they absorb 10 photons of radiation. So this is giving the relationship between these two, therefore it is quantitative in nature. And this ratio, that is the ratio of the number of molecules that are excited is equal to the number of photons absorbed. This ratio, number of molecules excited or number of molecules which absorbs the photons, to the number of photons. The number of molecules which are excited by the absorption of number of photons is given by the term quantum yield, which we will discuss later in detail. And see, for one quantum of energy absorbed, that is energy, if suppose A is a molecule, if it absorbs some radiations, it gets excited to higher electronic states. So this is primary process. This is primary process, and the activated species may or may not undergo chemical change in the secondary process. Therefore, this law is mainly concerned with the primary process only, and the energy absorbed by each reacting molecule is given by E is equal to h nu, and the energy absorbed by 1 mole of the reacting molecule, suppose if 1 mole reacts, that is given by NH nu. Okay, and we know that mu is equal to C by lambda, frequency is equal to velocity of light by wavelength. Therefore, E is equal to NhC by lambda. So the energy absorbed by each reacting molecule is given by the equation E is equal to NhC by lambda, where N is equal to Avogadro number. N is equal to Avogadro number, and we know that this is equal to 6.023 into 10 to the power of 23. And C is equal to velocity of light, and this is given by 3 into 10 to the power of 10 centimeters per seconds. Okay, and H is equal to Planck's constant. H is equal to Planck's constant, and this is given by 6.626 into 10 to the power of minus 34 joule seconds, Planck's constant. And the mu is the frequency of the radiation that is absorbed, frequency of the absorbed radiation, So in this way, they have given the equation for the energy absorbed by each reacting molecules. And by substituting all these values in the above equation, we get energy is equal to 119.7 into 10 to the power of 6 by lambda x per moles, or it can be given as 2.86 by lambda calories per mole. Suppose if lambda is expressed in angstroms, okay, we know that 1 angstrom is equal to 10 to the power of minus 8 centimeters. Therefore, the energy can be given as 2.86 into 10 to the power of then into by lambda into 10 to the power of 10 calories per mole. Or if for this 2.86 by lambda into 10 to the power of 10 into 10 to the power of minus 3, that is kilocalories per mole. In this way, 2.86 into 10 to the power of 7 by lambda kilocalories per mole. The energy can be calculated by using this formula, that is E is equal to NHC by lambda. This is the energy absorbed by each reacting molecule. In this way, we Stark and Einstein explained the absorption of photons by the molecule, and energy possessed by 1 mole of photons is called as 1 Einstein. This is just we have discussed now. Next, quantum yield. What is quantum yield? That is, here in the Stark-Einstein's law, we have seen that the number of molecules that are undergoing change. See here, each atom or molecule is excited by the absorption of 1 quantum of radiation. So, the ratio between the number of molecules that are excited to the number of photons absorbed is called as quantum yield. Okay, and with this I conclude today's session, and I would like to explain quantum yield and the types of quantum yields in the next session. And in this session we have discussed about the basic or introductions, what is electromagnetic radiations, how the molecules are absorbing radiations, and what is happening after the absorption of radiation. And we have seen the difference between the thermal process and the photochemical processes. Next, why UV and visible radiations are effective in producing the photochemical changes, we have seen. And we have seen the basic laws of photochemistry which governs the photochemical reactions, that is Grothes-Draper law and Stark-Einstein law. With this I conclude today's session, and in the next session we will discuss about the topic quantum yield, which is the most important topic from this lesson. Thank you.